In the second video, we're looking at methods for defining locations on the Earth's surface. What do we mean by locations? Well, some locations are kind of arbitrary, like where four states come together. This is Four Corners, the only place in the U.S. where four states meet. And we can find that on maps pretty easily. But what if you were trying to represent a location like the corners of a piece of property, maybe that's in your family, where there may not be markers or may not be really anything obvious that shows where something is? How could you do it? Well, we have a system that we use that's kind of based on the same type of coordinate systems that you may have used if you've taken a course in math, in particular in geometry. So let's take a piece of graph paper. So this image is like a piece of graph paper where you have an x-axis representing locations to the left or right, and a y-axis representing locations up and down. And we could simply plot some coordinates. So we count over 5 lines for the x-axis and we go up 2. We get a coordinate of 5, 2. So that seems pretty simple. Well, when you apply that to the Earth, it's a little bit more complicated. And one thing that makes it more complicated is the fact that the Earth is not flat. It's actually something that's nearly spherical. We talked about that a little bit in the first video. So the Earth is round. And when we're representing Earth coordinates, in most cases, we're representing those coordinates on something that's flat, like a piece of paper, or a computer screen, or the screen of a mobile device, like your smartphone. So that does introduce the potential for some error. But let's take a look, before we get into that error, let's take a look at how these coordinate systems are used for actually plotting places on Earth. And some time ago, some scientists came up with this idea of the latitude and longitude system for plotting Earth locations. So in creating the latitude and longitude system, they were looking for some reference points to sort of begin the system. So to have sort of an origin similar to that graph paper example we looked at a minute ago. So they could have used the lower left-hand corner, I suppose, of this plot that's sort of laid out over the Earth. But instead they chose a reference line exactly halfway between the North Pole and the South Pole to work as the x-axis, and then they picked another location, kind of an arbitrary location, if you will, that runs north and south. A little story behind it: when the scientists were meeting and trying to decide where the location would be for the y-axis, or the lines that represent what we'll talk about in a minute called longitude. There were representatives from Germany, there were representatives from France, the US, a lot of countries, the UK, and of course the Germans wanted Berlin to be the central point, or the origin point for the y-axis. The Americans wanted Washington, D.C., the Brazilians wanted Rio de Janeiro, the French wanted Paris. In the end, the British won out, and I'll tell you why that is in a little while. A little bit later in this video, I'll talk about why it is that they decided to use London, or more specifically, the Royal Observatory at Greenwich, to be the origin point. So here's our origin point for latitude and longitude. And the way they set up the system, we know that a circle has 360 degrees. So they set it up so that a degree in the latitude-longitude system for longitude, they would have 360 degrees that went around the circumference of our planet at the equator. And there's also 360 degrees that goes all the way around if you go from pole to pole. But if you're just looking at one side of the Earth, here we have, you can see it, 360 degrees of longitude, and this line on the left and right is really the same line if we wrap this thing around and we formed a cylinder. So that's the 360 degrees of longitude, and we'll get into what longitude is in just a minute. And then there's 90 degrees of latitude north of the equator, all the way up to the North Pole, and 90 degrees of latitude to the south of the equator down to the South Pole. So we'll look at this graphically so you can sort of visualize this a little bit better. Before we do that, though, a couple of terms. We use the term parallel to refer to lines of latitude, lines that measure your location north or south of the equator. So this red line right here is the equator that you see on the left diagram. So that would be a line that's drawn exactly halfway between the North Pole and the South Pole. And then every other line that's black on this left-hand image is a parallel. So those are parallels. They run parallel to each other, and that's where they get the name. On the right, lines of longitude are called meridians, and lines of longitude always run from the North Pole to the South Pole. So those are two terms that we'll use throughout the semester. We'll talk quite a bit about parallels and meridians, and a little bit later. But just so we're all on the same page in terms of the words that are used for describing these lines. Okay, moving on. Here's just for fun. Here's the Royal Observatory at Greenwich, England, and you can go there. It's not far from London, and you can stand in the Western Hemisphere and the Eastern Hemisphere at the same time. You can straddle the two, and there's 0 degrees longitude that runs right through the Royal Observatory at this very point shown in the photo. Okay, so how does this system work? Well, let's start with looking at longitude, defining longitude. So we know that lines of longitude or meridians run from the North Pole to the South Pole. They represent your location east or west. The origin point, or 0 degrees longitude, is the prime meridian. So that's what we call it, the prime meridian running right through the Royal Observatory at Greenwich, England. And let's make it a little simpler here. So we're just showing the North Pole and the South Pole and the prime meridian. And every other line of longitude is referenced against the prime meridian. So perhaps an easier way to look at longitude would be if you were viewing the Earth from space and you were looking from above. I know that's kind of a relative thought, above. If you were looking down on the Earth so that the North Pole would be in the center, so you're sort of looking down from space on the North Pole. So here's the North Pole, the center of this diagram on the right, and there we have the prime meridian. We're looking at only the prime meridian extending to the equator, so only really half of the Earth, the northern hemisphere, if you will. And notice that each of these numbers here represents an angle measured against the red line, which is the prime meridian. So this 45E right here, that's a 45-degree angle. If you measure the angle of that line relative to the prime meridian, that would be the longitude here drawn on the outside of this circle. 90 degrees would be a 90-degree angle, and so on. Also notice that we have 180 degrees of east longitude, or half a circle, and 180 degrees of west longitude, and that the east and west are designated by an E or a W. So whenever you represent longitude, you have to add the E or the W, unless you're talking about the prime meridian, which is 0 degrees, or this other line that's directly opposite from the prime meridian called the international dateline. That doesn't get an E or a W. It's just 180 degrees. Okay, so I think you get some idea of how we represent longitude. Now, the international dateline. So going back to the story, why did they pick Greenwich, England for the location for the international, or for the prime meridian? Well, they did so because the line directly opposite on the other side of the planet from the prime meridian would run through the Pacific Ocean, and it wouldn't cut a country in half. And we'll talk about time zones a little bit later, and you'll see why it's important for the country that you live in, or the place you live in, not to be cut in half by the international dateline, because days begin and end there. So here we have the international dateline. It does run through some nations of Melanesia, Micronesia, but it's pretty much out in the Pacific, in the middle of the Pacific Ocean. So it's not cutting through the middle of a continent. Okay, let's turn our attention to latitude. We're measuring your location north or south of the equator. So we have, once again, just to review, 180 degrees, a total of 180 degrees of latitude, 90 degrees in the northern hemisphere, and 90 degrees in the southern hemisphere. And we measure locations here on the outside of the Earth and the surface of the Earth by the angle between the equator, shown here in red, and the surface of the Earth. So whatever that angle is, in this case 45, we draw a parallel all the way across the Earth, and that's the 45th parallel. So if we wanted to be precise there, we'd have to add an N to that number. So we would be saying 45 degrees north. And here you see some parallels that are kind of important. Before we do that, let me just show you one more angle. Here's 66.5 degrees north. This forms the parallel known as the Arctic Circle, and we'll talk about why the Arctic Circle is important a little bit later, but just some examples of some parallels. By the way, if you're wondering why we put a parallel at 23.5 degrees north and 23.5 degrees south, here's a sort of a fun factoid you can think about. If you've only lived in Stillwater, have you ever seen the sun directly overhead? Have you? Directly overhead. I'm not talking about high in the sky, but directly overhead. We know that the sun is highest in the sky at what time? About noon, right? So next time you think about it, go outside, or if you're outside, look up if it's around noon and see how high the sun is. It's never directly overhead. And that's because the only place on the planet Earth where you will ever see the sun directly overhead is between these two lines, between the Tropic of Cancer to the north and the Tropic of Capricorn to the south. This is a zone known as the tropics, and we know it's pretty warm in the tropics. And that has to do with a lot of solar radiation received because the sun is so high in the sky. Okay, let's move on. So we know a little bit about latitude and longitude. What about if you need more precision in identifying an Earth location? So if I just say 36 degrees north latitude, that's not very precise. I mean, that's kind of, we need something that would help us break up 1 degree of latitude, or longitude for that matter, into something a little bit smaller so we can represent with greater precision our location on the Earth's surface. And we do that with minutes and seconds. So we know that 1 degree of either latitude or longitude equals 60 minutes, and 1 minute of latitude or longitude equals 60 seconds. And that's how we break it up. So if we want to represent a location on Earth with greater precision, we could say 32 degrees, 45 minutes, 12 seconds north. Remember, we have to add the N or the S, designating our location north or south of the equator. And then 102 degrees, 58 minutes, 44 seconds west. Now, if you want to try something fun, and you have a smartphone, and I know this works on, I have an iPhone, so I'm not sure if it works on Android, but there's an app on my iPhone called Compass. And it's one that comes with the phone. Pull it out, try that app. Maybe there's a similar app on the Android if you have an Android smartphone. And you can actually see latitude and longitude represented. You may have to go outside to get it to come up, because if you're inside a building, sometimes the satellites that the GPS or global positioning system satellites are blocked. So try to take your phone outside, but try it, and you'll see latitude and longitude represented on that Compass app, and it'll actually change as you're moving around because you're changing your latitude and your longitude. And I just threw on this last thing. If some types of apps and other systems that display latitude and longitude display them in decimal degrees, so it's pretty easy to go back and forth between degrees, minutes, and seconds and convert into decimal degrees. So a decimal degree is just another way of representing degrees, minutes, and seconds. And just for fun, here's some. I just put on the degrees and minutes for some places in Oklahoma. So here we have Stillwater. We're roughly 36 degrees, 10 minutes north latitude, 97 degrees, 5 minutes west. So remember, you have to add the N and the W, so don't forget. Okay, a couple of other terms. What are small circles and great circles? Well, a small circle is defined as any place on the planet, or I should say a line drawn on the surface of the planet, where you take a flat plane, so a flat plane like a piece of paper, and you make it go through the sphere at other than the center. So what are some examples of small circles? If we're thinking in terms of latitude or longitude, let's talk in terms of latitude for a moment. What are some small circles we just talked about, we just displayed? Well, we know the equator isn't one, because that would be if you take a flat plane and pass it through the center of a sphere, and that would be a great circle. So the image to the right is a great circle, and the equator is a great circle. So some examples of small circles would be Arctic Circle, or the Tropic of Capricorn, or any parallel other than the equator. So those are all small circles except for the equator. So how about great circles? Well, as I mentioned, the equator is a great circle. So is the prime meridian, and if you add to the prime meridian the line on the other side of the planet called the international date line. So the prime meridian and the international date line together form a great circle. So that would be as if you, again, take a flat plane, pass it directly through the center of the Earth. So there's a whole bunch of meridians. Every meridian and its pair on the other side of the planet forms a great circle. There's only one great circle corresponding to latitude, and that is the equator. How about this? What does this look like to you? This is the Earth. It's illuminated. We know something about the Earth. Only about 1/2 of the Earth is illuminated by the sun. So we call this the Circle of Illumination. And you guessed it, it forms a great circle. So where you draw this line this line going all the way around the planet, including the other side that we can't see, this is a great circle. So something else about great circles that are sort of interesting and important to things that we do all the time. In aviation, when airplanes fly long distances, they always fly great circle routes because they are the shortest distance between 2 points. So let's take a look at that in this next slide right here. So let's just say that you were planning a flight, pretty ambitious flight. You're going to fly from San Francisco in California, over here, all the way to Dubai in the Middle East, part of the United Arab Emirates. So you're going to go to Dubai. Maybe it's your first trip to Dubai. You're all excited. You're going to fly in a big jet, and it's going to be a direct flight. Now, does this look like the route that you would take? Perhaps. So if you're plotting out the route, you're looking at a particular kind of map, and you might think, okay, my route's going to take me over the central part of the U.S. It's going to take me over the east coast of the U.S. It's going to take me over maybe Morocco, Libya, maybe over this part of Saudi Arabia to Dubai. Well, would it really take you in that route? And that's where maps can kind of throw you off a little bit, including the map that we're looking at in this image right here. And in fact, you wouldn't take that route because that's not a great circle route. Even though it's represented by a straight line, here's the great circle route. And this is represented by an appropriate map projection. We'll talk about map projections a little bit later in the next module. But this is a map projection showing a great circle route as a straight line, just like it would be if you had a globe. So if you have a globe at home, grab it, pause this video, go grab your globe, take a rubber band or a piece of paper, a string or a piece of paper, and stretch it in between San Francisco, the approximate location, and Dubai. And you will see that the route doesn't take you over the eastern U.S. It doesn't take you over Morocco. It takes you over the North Pole, which is sort of interesting. So that is a great circle route, or the shortest distance between 2 points, and that's what airplanes fly because who wants to waste fuel nowadays with how much fuel costs? All right, let's turn our attention a little bit to something else that's related to longitude, and those are time zones. And in fact, our system of time zones is based on the longitude system. We know that circle has 360 degrees, okay, and we know that a day has 24 hours. So when folks were trying to determine what or how the time zones would work, they decided to have one time zone per hour for the 24 hours of a day. And what that gives us is one time zone for each 15 degrees of longitude. So we divide 360 by 24, we get 15. And in fact, each time zone in the world today is centered on what's called a principal meridian. So every 15 degrees longitude, that meridian is a principal meridian. So we have the prime meridian here in the middle, 15-degree meridian's a principal, and I've centered this blinking blue. If you can see it, it's centered on the 30-degree principal meridian. So let's zoom into that just for a minute, and you can see over the 30-degree principal meridian, we have 7.5 degrees of longitude on either side, and that is a time zone, essentially. So everybody living in that area, approximately that area, would be in the same time zone. If we apply it to the world, here's a look at the world and the way time zones are set up. Now, one thing you'll notice is these red lines, which actually represent time zones, are not straight. And that's because some countries have decided that they don't want their country split between two time zones, especially big ones. So they've kind of manipulated the line a little bit so that they're included in one time zone or another. Now, there's some countries that are so big that they're in multiple time zones, and you can see Russia would be an example. Russia stretches across a whole lot of time zones. The U.S. has a number of time zones, and we'll talk about those in a second. There are a few countries that don't recognize anything but one time zone. So China made the decision to have everybody, even though the country's pretty big, everybody is in one time zone in China. So let's take a look at what happens with time zones. So the time zone system is all referenced against what the time is at Greenwich, England. We call that Greenwich Mean Time, by the way. And you see these pluses and minuses. So you see this time zone. We see the time zone that's centered on Greenwich is time zone 0. So that's centered right over Greenwich, and there's once again 7.5 degrees of longitude on either side of Greenwich. And then the next time zone over has a +1, and that means that if you want to know what the time is in Greenwich, in the Greenwich time zone, or what Greenwich Mean Time is, you would add 1 hour. If you're located to the east of the time zone where Greenwich is, you'd have to subtract 1 hour. So you can see, I'll sort of advance and subtract this. Here we are going sort of back towards the U.S., and there is the central time zone that we're located in. We're 6 hours behind Greenwich, and if we go the opposite direction, we're going to be ahead of Greenwich Mean Time. Now, what this obviously this has implications for air travel, but also for, among other things, business and telephone calls. So you don't want to call, your friend in Europe at 7 o'clock at night Central Time Zone, because you're probably calling them, and it's probably pretty late in Europe at since they're 6 hours ahead of us. It might even be the person you're trying to reach might even be getting up for the next day. Okay, so what about time zones in the U.S.? Well, we have here's the Eastern Time Zone, Central Time Zone, Mountain Time Zone, each separated by about an hour. And notice that even in the U.S., time zones kind of jog and weave a little bit. We have the folks in Tennessee and Kentucky that are actually split between the Eastern and Central time zones. That's not very convenient. Oklahoma is in just one time zone, except for there's one city you might know about this one, located way out on the panhandle of Oklahoma called Kenton, Oklahoma, that actually they've elected unofficially to be part of the Mountain Time Zone because they have more of an affinity with Clayton, New Mexico, and Santa Fe and Albuquerque than they do with Oklahoma City or Tulsa. They're a little bit closer to Clayton, New Mexico, so that's the decision that they made. But anyway, we have Alaska in a time zone, and then the time zone that's the farthest west is the one where Hawaii is located. Okay, the last topic I like to deal with in this video, I want to talk a little bit about what happens with a day, where a day begins and where a day ends. So the birth of a day and the end of a day. And to do that, we're going to take a look at the Earth from, if you will, from above, looking down on the North Pole. So here's the Earth right here. You can see Greenland. There's the North Pole approximately. And I've marked a couple of things on this image. The red line represents the prime meridian, and the greenish line represents the international dateline. So we're going to go through a series of views of the Earth, and we're going to discover and talk about what happens, how a day begins on our planet and how a day disappears on our planet. Okay, so we'll go ahead and kind of make it simple here. And again, the center of this image is the North Pole, and the outside of that ring is the equator because we're looking at just the northern hemisphere. So that's just to give you a perspective of where we are. Okay, so let's talk about a situation where it's noon at the prime meridian. When it's noon at the prime meridian, this first image right here, which says Sunday noon, there is only one day that exists on the entire planet. So anytime it's noon at the prime meridian, only one day exists on the planet Earth. And 1 second after noon, we see a new day begin to appear, and it appears at the international dateline. So 1 hour after noon, or 1 p.m. at the prime meridian, we've got a little sliver of Monday that started to appear. So most of the planet is still covered by Sunday, but we have a little sliver that corresponds to Monday. So let's continue to advance things. At 6 p.m. at the prime meridian, about a quarter of the planet is Monday, and about 3/4 is still Sunday. And I think you get the idea. Here's 9 p.m. at the prime meridian. Monday is not quite halfway there, but at midnight at the prime meridian, the Earth is equally split between Sunday and Monday. And then as Sunday begins to disappear, at 11 a.m. on Monday at the prime meridian, we have a tiny sliver of Sunday that's just about to disappear. And once again, we'll return full circle. Here's Monday, noon at the prime meridian, just Monday existing on the planet. And the very last image is a little sliver of Tuesday as it begins to creep onto the planet. So